Hi everybody! Today we're going to be working on a video that I've been looking forward to ever since I got my hands on this piece. This is a VFD, and we are going to take it apart and see what's inside. So I'm Alex, and welcome to the Renaissance Builder. Now like I said, this is called a VFD. Now VFD stands for Variable Frequency Drive. Now what that means is that as we've been discussing, in fact, I can take this here picture and I can show it to you. I can use this. This is a picture I just used. Let me get a marker. Is my marker in here? Yep. All right, cool. So we're going to erase some of this, right? So a VFD, variable frequency drive. Now what that means is you have to remember that the electricity coming out of your wall, in fact, all electricity that we use standard is called alternating current. Alternating current is basically DC current that switches from positive to negative a lot. So remember the sine wave? Zero. Sinusoidal sine wave. Technical term for you. All right, so again, that's our sine wave. We got positive and negative, and its DC voltage is just switches a lot. Now, the amount of times in 1 second, which in America is 60 times a second that it will do this, that's called frequency and is measured in hertz. So the amount of times per second switching is called hertz, also known as a frequency. Oh, this is my writing's terrible, but whatever, you get the point. Either way, it's a frequency. In America, the frequency normally runs at 60 hertz. Now, this frequencies apply to everything in life. In fact, there's even a study, a long buried study, that Nikola Tesla kind of dredged up when he was playing with his large-scale planetary electrical transmission network, that he thought, so the ionosphere around the planet actually pulses. And so he thought that if we could add energy to that pulse and we could change the frequency at which that pulse basically orbits the planet, then we could add energy in one place and then take that energy from another place. And the way to do that would be to pulse the energy up into the ionosphere, which is why he built that massive tower to wirelessly transmit energy. But what he found is that it pulses at 8 hertz. And another thing that he ended up finding, and this is kind of that whole black magic territory or whatever you want to believe, the other thing he ended up finding is when you change that natural frequency from 8 hertz, you actually start changing behavior patterns in living beings, including humans, Homo sapiens. So, like, that's not proven science, at least not that I know of. You know, I'm not saying it was aliens, but it was aliens. Yeah, I love that scene. Anyhow, off the subject, I totally digressed on that one by a lot. Frequency, we are using 60 hertz. Now, a very common way to run motors these days in a variable speed fashion is to take that motor that normally runs at 60 hertz and we run it at, say, 30 hertz. So it'll do this 30 times a second instead of 60 times a second, which basically slows the motor down because we're feeding it half the time. If you think about it like this, every time this voltage goes up, we're using a magnetic field to kick the rotor in the direction we want it to go, right? So if we kick it 60 times a second, it's going to go at a certain speed. If we kick it half that much, so only 30 times a second, it's going to go slower. That's the general idea. And if you kick it faster than that, which does happen, then it'll go faster. Now, the way this works is we feed it the standard 60 hertz sine wave. Then we convert that to DC through a full wave rectifier. Full wave rectifier, I'll draw it out here quickly. Let's see, and then this and then that. So this to there, this to there. It's a bunch of diodes, 4 to be specific for single phase. All right. Boom. Nope, I did these backwards. These have to go this way. Diodes, all right. This is going to be negative. This is going to be positive. And what we're actually doing is if I change this and I make this my 0 form, you know, our 0 line, what this rectifier is called a full wave rectifier or a full bridge rectifier. Terms vary. But what this is actually going to do is it's going to chop off this bottom half and it turns it into essentially this. So we just end up with a bunch of positive pulses, right? Well, I mean, you know, measured off the positive end of that. So then we add some capacitors. So the capacitors store energy, right? And we knock off the bottom end of this because we're feeding it the capacitors. And then we put some chokes and stuff in there so that by the time we're done, we have a good DC voltage. Then we take that DC voltage and we send it through we send it through a bunch of fancy transistors is really what it amounts to. And those transistors turn on and off like a lot. So then those transistors, what they're actually doing is pulsing the on signals like, you know, they're pulsing the signals like that. And then when you want to go to DC, it drops down here and it pulses this signal. All right, it's a really messy way to do it, but you get the idea. We go from AC to DC and then pulse that DC to mimic a sine wave. Now, that's a real quick explanation. It's a real dirty, quick explanation, but it gets the point across because there's a couple things in here that I want. There's a diode rectifier for the input control of this to turn the AC into DC. There are output fancy transistors. They're called IGBTs, insulated gate bipolar transistors. So I'm just going to call them fancy transistors. So those transistors I can use. Like say I want to play with our Jacob's ladder and I want to see if I can get these transformers to maybe overclock the transformers. I just said that and it works. So I can take the hertz, instead of feeding it 60 hertz, we can use these IGBTs and we can, you know, change it to run, instead of 60 hertz, we can run, say, 70 hertz or 80 hertz. This here unit is running like 56,000 hertz. That's a lot of times a second. I don't think we're going to get to that because I believe, I'll have to check the technical specs, but we're limited. We might be able to get like 20,000 hertz. But either way, you get the idea. We're going to try overclocking the transistors, but that's a long ways away. So today, I just want to take this thing apart and see what's inside and see if we can't test some of these components to see if the things we want are still good. So let's get started. Okay, now this here, like I said, this unit is broken. There's something wrong with it. So it let the magic smoke out of the box. And we are going to use our handy dandy screwdriver and start taking things off. So there's usually like a plastic cover around this that surrounds the whole thing. And that's not here. No biggie. Big whoop. Now, there are some things you have to be very, very, very careful with on these things. Now, this thing hasn't been energized in quite a long time. So the chance of it still holding a charge is pretty slim. But that being said, there are very powerful capacitors in these things. This thing being rated for 23 amps tells me that there's very, very powerful capacitors in here. And basically, we don't want to discharge those capacitors on ourselves. So you got to be very careful with that. In fact, here's a sticker. Oh, there's a screw under that sticker. Look at that. They put a sticker that says, warranty void if that sticker's broken. In this case, that might actually hold up, being a commercial piece, but there's already legislation out that says those stickers don't carry any weight, like none at all. They're just a distraction, essentially. So we have some plastic pieces here. Got to get up under there and get the plastic away from the knob so it can set. There we go. All right. Now, we have a lot of electronics attached to the top of this. I don't give a about these electronics. I couldn't care less. What this normally does is these electronics are responsible for holding programs, giving you an interface to be able to change settings, set points, and all the stuff that actually make this thing do what it's supposed to do. I don't care about them because I'm probably, at least my idea is to use an Arduino and create my own control system. So that's why I don't care about them. Looks like I need to get this plastic out of here somehow. Oh. Ta-da! All right. So, here it is. That is what blew up. I don't know what that was. Oh, no, I see. So the traces on the board have exploded. All right. Going to be some camera shake. I'm going to take the camera, get a picture of this for you guys. Okay, so you can see right there, right in the middle of the screen, all that blackened and burnt looking stuff. So it looks like the traces or the metal pieces on the circuit board have actually just straight up evaporated right off the board, which means they were drawing too much current. Now I'm sure there's going to be other damage that would have caused this in the first place. Everything else in here, whilst dirty, here's your capacitors. What rating are these capacitors? 300, focus. Wow, it really did not want to focus there. 385 volts, 560 microfarads. I kind of expected more, but that's the general idea. So we're going to keep digging in and find out what caused this damage. You know, I have to say, through this whole project, well, actually, I have to say, the last while, I've been using this Rode Wireless Go microphone system for a while, and I absolutely love the thing. Like, I can stare at the little screen right now and tell my battery levels and my input levels and the fact it's actually picking up what I'm saying. It's really neat. Well, enough about bragging about my Rode Wireless Go microphone system. So, first things first, what you want to do when you're working on something like this is you just put eyeballs on it. You look at it. You say, would you look at that? Would you just look at it? Would you look at that? So the idea is anything that is obvious, anything that could hurt you, avoid it. Like, don't touch that, is really what it comes down to. Looks like there's a fairly decent resistor here that I might be able to use for something else, but there's only one of them, so that doesn't really do me a whole lot of good. There's a couple relays in here. Those are good. So we've got our cables. I don't know what these go to yet. Can start getting my multimeter out and figuring out. But what I'm going to do is, you know what? There's some funky looking bits. I might just have to, looks like there's some Torx bits in here, or star bits, or whatever they want to call them. So I'm going to unplug the low voltage control setup. So again, the digital stuff, whatever, when that exploded, it just plastered the back of that with soot. Yeah, that went pretty good. So I don't care about that, like, at all. All right. So it looks like those wires go down underneath, and it looks like right under here is where we have, right underneath this is where we have our IGBTs. So let's start seeing what's going on here. Now, we've got some pretty serious capacitors here. They probably have a lot to do with the input filtering. a fairly heavy-duty transistor and some chokes and these here wires. Okay, what does this one go to? So that's just a jumper to there. That's a fancy relay right there. Is this a relay or a diode? What does the board have it marked as? C85. That might actually be a capacitor. All right, let's start seeing if we can get this off. First of all, let's see what happens when I actually try to take that. Yeah, I didn't think so. So I'm going to get my handy dandy iFixit kit. No, iFixit is not a sponsor, but I love the kit. So we're going to get out our handy dandy iFixit kit, Protect Toolkit. I should put a link to it down at there. Nope, the YouTube won't let me. I'm not big enough yet. All right. So I have, is this bit big enough? That bit is too big. So how about this bit? Is this bit big enough? That bit certainly is big enough. So we're going to use this to take this screw out. Gotta love it. iFixit Protect Toolkit, peoples. Works like a champ.
Now you probably notice I'm being a bit careless with the screws. And a lot of that is because I don't have any intention of putting this back together. I in fact intend to tear apart this board and totally use the pieces off this board for my own intentions. Like I said, my idea is to overdrive these here 12,000 volt transformers, which I think would be awesome. Like, super awesome. Screws, that's plastic. Is that a plastic screw? It is. Well, that's odd. I bet there's a reason. I don't know what that is, but I'm sure there's a reason to having a plastic screw in there. Yeah, that's just a plastic screw. Okay, what else?
All right. Ta-da! And there you have it. There is our board. Okay. Now, here's what I'm going to do. We have the back side of the, this is for the most part just a heat sink. There's a transformer in there too. But for the most part, that aluminum piece is just a heat sink. We're just going to set that to the side. Try not to get thermal paste all over everything. Now these IGBTs, so this right here, this here section right here is the IGBTs. At least I'm more than positive that those are the IGBTs. But these capacitors could still be charged. So what I'm actually going to do is check for voltage to ground. None there. All right, and there's a reason for that. I don't want to get bit. I don't want to get electrocuted off these bloody things. So, safety first. Check to make sure you're not going to get electrocuted. Okay, so the capacitors are dead. All right, MKP62. Metallized polypropylene film interface suppression capacitor. Woo! Okay, that's a big word for capacitor. So these are capacitors. That to there, that to there. Yep. It looks like my rectifier is probably built in to this whole IGBT pack. Okie dokie then. Alright. So at this point, I'm looking at needing to desolder some stuff. And I'm not exactly prepared to desolder some things. But this is definitely, well, this is definitely interesting. I guess what I'll do is I'll keep working on desoldering some of this stuff off camera and hopefully get some of it taken apart, because I'll be honest with you, I do not have a good soldering setup. I mean, I literally have one of those Weller 110 volt pistol soldering irons, and I mean, it gets the job done, but all right, so a couple seconds later, yeah, I had time to change my shirt and do all this other kind of stuff in a couple seconds. I'm not that fast. Anyhow, confession time. I have royally effed this thing up. I'm actually kind of embarrassed, but you know what? I'm just gonna own it. I do not have the right equipment for desoldering. I don't have solder wick. I don't have one of those desoldering suction thingies. I don't have any of the right equipment for desoldering. Not to mention, these things are actually like soldered on both ends of the board. Anyhow, so trying to get the IGBT pack off turned into, well, breaking the high power side of the board and getting some terminals off, and I think I broke one terminal and still have the control side on there. I'm probably going to take my Dremel and try cutting this out because, so I looked it up, and this is a $70 part. Just this white thing right here. That's a $70 part. Now, you might not think much of that, but in the world of electronics, that's incredibly expensive. So I really want to try and save as much of this as I can. So I'm probably going to take my Dremel and cut things apart and try to salvage this thing yet, but for now, it is an embarrassing situation, to say the least. Some components I do have. The capacitors I was able to save off fairly decently. I was able to measure them, and they're 560 farad microfarad capacitors, but I'm only reading like between 510 and 520 microfarads, so they're a bit off. Probably power surges and stuff have weakened them, but the resistance is still there, so I'm going to try using them yet, and they may blow up. I guess we'll find out. But I don't know. Every time I say something's going to blow up, it doesn't. So, whatever. I'm like going to have to put 1,000,000 volts to it or something and see if it blows up. Oh, I can do that. Well, I could put 12,000 volts to it at least. So, if you guys clicked on this video because you want to know what all the components are that are going on inside these VFDs, here's the breakdown. You've got a massive heat sink because you're dealing with a lot of heat, which also houses an output inductor. It's a filter to take out the spikes and stuff from the electricity. So you've got your electronics that control the thing to begin with. They do all the control and brain work happens in the electronics. Then you've got the main board, which consists of a rectifier, so 6 diodes built into the block, and then capacitors and everything to deal with what's going on here is dealing with your DC voltage. That trace or that DC bus goes right back to the IGBT section of this block, which then gets controlled by all the little pieces on here. So that's what happens inside of a variable frequency drive. Now, I'm going to continue, like I said, I'm going to continue to try tearing this thing apart, taking the pieces and creating experiments with these pieces. I really want that IGBT out because I want to try and use that. If I can use that IGBT to make a, I think it's up to 20,000 hertz is what that thing can run at. I have to look at the specs again, but anyhow, I can do some really fun stuff with that. Yeah, so that's what goes on inside a VFD. I want to thank you guys very much if you decided to actually watch this whole thing. So thank you very much for watching and seeing what was going on here. I really appreciate your participation. Feel free to leave some comments in there to see if you would have done anything differently, like have the proper soldering equipment. And how about this? Leave some comments with ideas that you have for these components. So I want to know what you guys would do with this stuff. Like, what projects would you make? And maybe I'll look into that of actually making the project. So leave comments in there, videos that you would like to see done using these components, and I will totally think about it and try using your ideas if I can. So thank you very much for watching. Hit a thumbs up if you actually liked this video. Make sure you're subscribed and hit that bell icon so you're notified of future videos. For example, if you leave an idea, and then you might as well make sure you're subscribed so that you can see when we actually do your idea, and make sure you come back for the future videos. By the way, I also have a Patreon site. If you want to go ahead and head to the Renaissance Builder on Patreon and become a patron, then you can help support future videos like this and make them better. Anyhow, thank you very much, guys. I appreciate it. You guys have a good night.
Bye-bye.